with Dr. Hermine Schnetler, and she's a distinguished engineer and academic with over 30 years of experience in systems engineering across defense, commercial, and research sectors. She holds a Bachelor of Science in Electronics Engineering and a Master of Science degree in Systems Engineering from the University of Pretoria in South Africa, as well as PhD in Software Engineering from Cranfield University in the UK. Dr. Schnetler has contributed significantly in the fields of optics and photonics, serving as the head of systems engineering at the Royal Observatory in Edinburgh. Her work involves defining and specifying detailed requirements for scientific instruments used by UK and European astronomers. She's also a visiting professor at the University of Strathclyde, where she advocates for systems thinking and innovative engineering education. A member of prestigious organizations like INCOS, IET, and SPIE, Dr. Schnetler is passionate about inspiring the next generation of engineers and advancing sustainable development through engineering. Dr. Schnetler, please start.
Thomas, yeah, thank you for the nice introduction. I think it's a little bit, maybe make me feel like it's a little bit more than who I am. I'm just a engineer by heart, but I hope that people will find this talk interesting. And I apologize up front if I go a little bit more like a lecture rather than just a normal talk. So the topic of the talk is how to deal with complexity and uncertainty by keeping a lid on requirements. So I think it's important to start with what is the definition of a complex system. And I'm not going to read the definition for you, but I think there are a lot of things that might imply that things can be complicated and introduce some complexity. And for me, that is when you have a great number of related but various elements, and that they are connected in a intricate relationship. And there are a lot of complexity research in applied and a wide field of fields. For example, software development. The big thing today is artificial intelligence. And also, I think the human body is, for example, bioinformatics and software engineering. There are a lot of complex things. And again, I do agree that when we look at nature and this earth and maybe the universe, things are really complex there. But and that's why I say example. You will see that in my examples of complex systems, there are absolutely no human-made system really there in step of maybe when you talk about the whole way how countries are working and how our countries are interacting with one another, but not in terms of our infrastructure, but in terms of the human beings. So for me, again, what I'm going for is to say that we could actually get rid of complexity by following the design principles and systems engineering. So that's where I'm going with this. And then my second slide is what is uncertainty? And to be honest, this is going to be a morose statement I'm going to make. And that is that we do not know, nobody of us know what the future holds for us. For example, in 2020, nobody really expected that we will have this worldwide shutdown and how it impacted us. It's out of our control. And rules are changing. The economy is uncertain. There's a lot of risk-taking there. I mean, at the whim of one single man, who I will not name, things can change overnight. Just before this lecture, my husband brought up to me a letter, and it is just my bank to tell me that in these uncertain times that my interest rate on my investment will go down. So you can see we live, our whole lives is based on we are facing risks all the time. And in my mind, this is the Maru's part, is that everything on this planet Earth is basically uncertain. And the only certainty I have is I know I'm alive and I have been born. That's a fact. And another, and this is the real sober note, is that once we enter this earth, we are already on a pathway to end of life. And none of us know how long our life's going to be. And for me, that's the only two uncertainties. So I think even before I go further, I think uncertainty is a fact of life. Complexity is something that we can manage. And that is where I strongly believe that if you use a common framework and everybody uses the same common framework, we can actually develop and produce products, systems, instrumentation that can provide us with real, maybe highly capable functionality and might provide us with data to solve complex sort of like natural sort of phenomena, like, for example, as we study astronomy, I mean, the universe is big, it is totally unknown, but we can come up with design of experiments, for example, and we can use this common systems engineering framework to develop instrumentation and infrastructure to really help us collecting the data so that we can sort of model and understand how things are put together in the universe. So we don't need complexity in our equipment and infrastructure to study complex topics. So for me, if you look at the whole history of engineering, I mean, it comes a long way. And I would say the father of technology is Graham Bell. There's a lot of people making different claims. But in the end, I think engineering really took off after the Second World War. And that is when they actually, the people really introduced the common framework. And another big step where the available technologies had a big impetus to grow and become available. I think there's one world activity or event that led to it, and that is the Second World War. And then secondly, the explosion of the population. The more people we have, the more brains we have, the more we develop technologies that can be used. And again, I think when they initially devised the systems engineering common framework, it was really, really good. And I also think, for example, a thought that I would like people to put down on their desk is asking the question and try solving the question. In 1961, the state president of the USA, John F. Kennedy, said that before the end of this decade, the Americans will put a man on the moon. And they did. And actually, before that, NASA didn't exist. So why did they manage to do that? And one, they had a lot of money to spend, a lot of resources to throw at the problem, but they did that in 8.5 years. And currently, I am working on, I'm the outgoing project manager for the Wide Field Imager for the new Athena mission. And if I look at the history of Athena before it became New Athena, that process has been going on for years and years and years and years, and was officially kicked off in 2014. Then they stopped it. So if you look at the time, we are already 11 years on, and still the mission is not flying. And I would say it is because there's a big misunderstanding of what systems engineering is and the common framework. That is one reason why we take forever. The second reason is again, you go back to my point that America managed to put a man on the moon because they had endless resources in terms of funding and people. So again, we are complicating our instruments and the way we're working because we have to create these vast, big consortia. And yeah, that provides you with more people. However, because we're not co-located and because we do have different ways of working, the common framework should be more important. But in my experience since 2005, when I joined the UK ATC, which stands for the United Kingdom Astronomy Technology Centre, every consortium that I've been part of, we spent so much time in defining the processes and how we're going to work. And then every project has to establish their own infrastructure, in terms of tools. And when it comes to tools, people love talking about tools and how the tools, which tool is the best, and we waste so much time. Instead, we should focus on the product we're going to develop. And I think that is the important point here. And again, the systems engineering framework, as defined in basically the IEEE or ISO 15288 and 12207, which is a system and software life cycles, if we all can just believe in it and really, if all our institutions can put those processes in place, and I'm not saying they there, we also should strive for making our processor more mature and get people to understand why they're doing things. That would be quite helpful. But if you look at this slide, the view graph I'm showing, stakeholders are of the utmost importance, and that is also where we get our money and funding. As I also mentioned, availability of technology is a good thing. And again, I think it is important to understand, especially if you work on a space, well, actually all project now, but space, everybody talking about technology readiness levels. And I do think it can be used in a sensible way, but my experience again in astronomy is we don't always use new technology. We are using existing components and devices in maybe, for example, in electronics in a different circuit diagram, but we aren't really developing technology because I think both ground-based astronomy and space astronomy are so risk averse that it's the wrong word to use. But either way, I think the systems engineering support processes are really defined in four groups, where you have your project processes, which is basically all about project management, and it is to do with planning, executing, monitoring, replanning. And it is basically an endless cycle, making sure that everybody is moving in the same direction. Then there are many technical aspects, and the technical aspects is the bit that I will focus on in a very simplified way to get to the point that I want to make. And then agreement processes, we all are constantly having to agree. Either we are supplying things to somebody else, or we are buying things from people. And that's what's meant by the agreement processes. All our institutions have processes in place for us to buy off-the-shelf materials, products, and so on, and then if you belong to a consortium, typically there's a memorandum of understanding or an agreement, who's supplying what, when. So that is all part of the agreement processes. And then enterprise. Now, enterprise is the bit where, because we are working in consortia, and each enterprise we are belonging to, maybe enterprise in this case, implies what is the better word for if you work in basically business, in the industrial sector and not research. But enterprise also could stand for our institutions and how each and every one in our institutions are working. Now, to get synergy, it is difficult because there's so many countries, different countries have different ideas and have different support processes. However, for each and every one of us to really to enjoy our work and be able to do our work, we have the basic processes of somebody is providing us with offices, desks, furniture, and IT equipment, and also how we're going to get paid. So there is finance. That is what's meant by enterprise systems. But I think what is important in development of an instrument or a system is that you need strong technical management to ensure that every activity needed is executed in a timely and cost-effective manner. And this should cover the total life cycle of the product. And there are inherent differences among hardware, software, and the human elements from a system that are constructed. And yeah, almost every present day system contains or is modeled by supported by computer-based technology. So you do not really actually get a software-only product, or maybe very little products where you do not have any intelligence included. There are still chemical systems, electrochemical systems, and mechanical systems which you don't need those controls. And I would say increasing complexity of human-made systems is mostly unnecessary, but also when you want to deliver a rich capability, for example, like today, global positioning systems, we all have it in our phones. And when I was working in South Africa in the defense industry, I worked on attitude and heading reference unit and in navigation, inertial navigation. And at that point in time, GPS was not available to everybody. So global positioning system wasn't available to everybody. And you can now see how we start. Our mobile phones, for example, is pretty capable of doing a lot of things. Surprisingly, the mobile phone was there to be used as a phone. However, most of us is not actually using it as a phone. Can anybody, or can you show with your sort of reaction who do use their mobile phone by phoning a lot of people and not the other functionality, or just like in a negative way, maybe, so I can see who use their phone still as a phone pretty much, but mostly as something else. You got my questions? Don't
Like,
see any.
About 90% of people here in the room are using phones for something else than phoning.
Okay. So that's my point. You can see the use case and how it has changed. Really is quite important. Yeah. So I think this is for me. The important point is that things are changing as well, but I think also what systems engineering is supposed to bring to us all is having this integrated systems approach, which is like also quite misunderstood because it is a structured, stepwise, iterative, interdisciplinary, and collaborative approach. So when I joined the ATC, the typical way of working was that the first person that would actually do any design and of their understanding of what is needed was the optical design, because UK ATC traditionally support basically ground-based astronomy. So the optical engineer will design the optics and then throw it over the wall to the mechanical person. And then suddenly we look at volume envelopes and the design doesn't fit in the volume envelope. And then these two guys, I call them guys, but it could be a girl and a guy, they would negotiate with one another and iterate on the design. And then again, if you do have things that needs to be controlled, the mechanical engineer will select the motors and will forget totally of sensors like a set 0 point micro switch or whatever, end stops. That will all be forgotten until the mechanical engineer throws the design over to the electronics engineer. And again, the electronics engineer and the mechanical engineer will have discussions, and the poor software engineer will only get the system description in the end, and then software engineer has to fix everybody's problems. So what integrated system approach actually bring together is making sure from the start, everybody who has an interest in the system will work together to make the best decisions in terms of the most elegant optical, mechanical, electrical, and software design. And when I talk about software, it could be also like VHDL for FPGAs or boot block software or whatever. And you have this approach with the aim to capture the stakeholder needs and their objectives, and to really to transform these into a system fit for use, and which both satisfy the minimum requirements and optimize the overall system effectiveness. It is really highly integrated and structured, and if applied correctly, it should be good enough to eliminate complexity and manage uncertainty. And I will try to show you as well what is the basis of this claim. And again, like similarly, I think there are two very important, well, actually, there's the development process, which is on the basically right-hand side of this view graph. And then you really need a strong configuration management system to deal with whatever complexities there are. But also the configuration system should be based on a workflow that supports every development activity. It's not an afterthought. And if you really think about it carefully, everything should start and end with the product breakdown structure or product tree, which is the end of the process I describe, or the end of the output of step number 6. So again, it is very important to evaluate your problem and need, bound the problem. Where is my system going to start and stop? For example, in WFI, which is the Wide Field Imager, we're part of the new Athena mission. I'm not responsible for the spacecraft. I get my power from the spacecraft. I'm not responsible for the downlink. So you need to know where you are in the whole system of systems. And therefore, that is where your external interfaces come from, by bounding the problem. And then I think it is important to perform a use case analysis. And if you guys are in astronomy or in science, the scientists need to really define their design of experiment. We need to understand what they want out of it. if we don't, we cannot really design something that's fit for purpose. Then for me, and this is again sad, if you go to the INCOSE Book of Knowledge, which is now, I think, the de facto standard for systems engineering, they spend maybe half a page on functional analysis. And I think functional analysis, if you skip that step, you are bound to leave out important functions you need. And therefore, for me, everything, like the whole process of how do I design something, is based on the functionality, understanding which functions you need throughout the whole life cycle of the instrument. Then your engineers should then implement functionality in hardware and software. And once that's done, and you will do it to a level where the systems engineer really can partition these solutions into subsystems by making use of the very simple rule that says, for each system, you should have high cohesion of functionality in it and low coupling. Why low coupling? Because that, again, reduce and simplify your interfaces between your system blocks. And then once you've done that, once you have your functions, you can derive and flow down requirements. And again, for me, people are put a lot of emphasis on the flow down of requirements. There are requirements that comes from the user that will flow down. But your in the end, a lot of your technical requirements comes from your solution, how you implemented the function in software and hardware. And again, that is 7 steps I believe strongly in, that determines everything. And for example, maybe a point to mention here, once you've developed your system architecture and you start building your product tree or product breakdown structure, whichever term you want to use, if you lay it out that it runs from left to right, and as you go, you get smaller and smaller blocks, and you go as far as where you can either make or buy components or modules or whatever you want to call it. And if you associate, again, with each of those products, the technical data to either to produce, manufacture, or buy it, then you would automatically get your timeline for your development. But that is a bit like, that is where the conflict management comes in, how you manage the important data for each and every component you need to build your system. So that brings me to the crux of the process. And yeah, conventionally, I maybe should swap things over, but for some reason, I started on the right-hand side, and we need to find user requirements, and we always do. Now, unfortunately, a lot of user requirements sometimes tell us how to implement things, but let's not get too bogged down into that. And another point that's extremely important, yes, some of those user requirements, as I already said, will flow down automatically. For example, the waveband in astronomy, because the astronomers now know what wavelength they are interested in, because the celestial bodies that they are going to observe, they emit at certain wavelengths, and for each of the science cases, that's what they want. But as I also say, a vast majority of requirements are coming from the architecture that you have developed. And for example, how I justify my case is that if you look at, for example, the square kilometer array science goals, and you look at the extremely large telescope science goals, it seems to me as a non-astronomer that we are trying to answer the same questions, but different approaches. And I don't think there's anybody in this room that would not agree with me that the way I would write the requirement specification for a radio telescope is rather different from how I would write it for a ground-based optical and near-infrared telescope. Anybody agreeing with me or disagreeing with me? Maybe. Anybody agreeing? Oh, no?
Yes.
Yes, okay, so sorry. This is where being in a room would be so much better, because then I can have some interactions. But either way, so you can see your user requirements go into your developing the system architecture, and all those little flow boxes tell you what to do, and that is perform a functional analysis. And you can see that also go into the analyze use cases, and the things on the left-hand side is really giving you data flow, control flow, timings, and things like that. While on the right-hand side, or in the middle box, the structural design. How would things look in terms of hardware items? And if you perform these steps, then at that point in time only, you can, after you have your physical architecture and behavioral design of your system or product, you can really write a product specification or a development specification. And I think that's the crux of the matter. Now, there are another important point that I need to mention. As I mentioned before, when I talk about bounding your problem, where your system starts and stops, that will define external interfaces for you. And then once you have your architecture, you will have system blocks that needs to interact with one another. And for any specification, the definition or the requirements on interfaces are essential, because no specification is complete without having your interface requirements or interface definitions available. Now, why are we talking about interface definitions and interface requirements? If you are busy developing two new blocks, building blocks, it doesn't matter at which level of your system it is, then the interface between those two blocks are not defined. So therefore, you need to place requirements on both of the systems. But also, if I go back one step, what is the definition of an interface? I think we sometimes just go too quickly to the implementation side and not thinking on the physical phenomena that needs to be transferred between system A and system B. And this could be electrical, electrons, photons, control, data, thermal, mechanical forces, whatever, how many ever physical parameters we have, it could be any of them. And then there's an interface boundary between them, element 1 and element 2. And I think that is how we should think about it. And again, you very quickly, especially if you work with electronics and electrical people, immediately they see an interface definition as connectors and cables. But that is the implementation of the interface. It's not a definition of the interface. So now the steps of how to demystify interfaces is really quite easy. First, you need to identify the interfaces. You can do that from your content diagram, your n-square diagram, and internal and external interface diagrams. And when you identify those, you can maybe say what type of interfaces it is. Is it electrical? Is it structural? Is it thermal, or whatever? Is it a chemical reaction? You need to decide, data, whatever. And then you need to define these interfaces. And then step 3 would be as indicated in the view graph, you would then basically write the requirements. And I think I have made a mistake on my slide. Apologies for that, because you need to have different descriptions, because you need to see it from two sides if this interface belongs to two different people. And I think another thing, determine the ownership of interfaces is very important, because if you have two elements and there's no interface defined, make sure in your project or development project, you nominate somebody who take ownership, define it, and then once it's defined, the two people can then discuss and come up to a solution to define this interface requirement for you. So I think it might seem a bit like, why am I talking about interfaces? But keep in mind, your interfaces governs the interaction between system blocks and between your system and the external world. And that is very important, because if you don't get this right, then you're going to struggle a lot. And maybe, I can relay experience I had. That's not in astronomy and research, but I was working on a sighting system for a helicopter upgrade. And again, it was a crazy project with basically, we were supposed to deliver from the kickoff, delivering a first prototype to the helicopter for integration. And I had a very, very good systems engineer in my team. And we slipped by 1 month. We were, we delivered after exactly 10 months, keeping in mind that the 10th month was actually during the summer period, December in South Africa, where everything shuts down more or less from the 16th of December, and everybody's on summer holidays, sand, sea, and sand and sea or whatever. And we delivered in January, and within 2 hours after bolting the sighting system and installing all the electronics, the sighting system was fully functional. Why? Because the interfaces was so well defined and everything just worked like clockwork orange. That is one of the nicest experience ever to have. So following that, I think it's also very important that your requirements from the user side, obviously, you need to go from user requirement and get your architectural design. But your design will determine cost, risk, ease of implementation, and quality. So if you control if you come up with a simplified design, don't go for complexity. Make it as simple as possible. And again, I always think about it. Use what you have. Don't invent difficult things just for the sake of complexity. Think carefully what you need. And then the operational requirements, environmental availability, physical characteristics, all of that should be captured in your system development specification. And if you get that right, you have something that's fit for purpose. But I cannot stress how important it is when you do your design, think about every solution, think of how difficult or how easy would it be to implement this design. So now I am going to really go quickly through an example, because again, people are always asking, can you give us examples of the things I'm talking here about? So because I'm working on the wide field imager, and again, if you are working on a science instrument, and in this case, astronomy, you can see this very simplified but complete process flow diagram of, observation preparation, validation of the observation, and then scheduling that observation. Then in terms of like when you have a satellite like New Athena, you would upload your commands, and then you will execute the observation and also send telemetry back to the mission operational center. And again, you will also send that will end up in a data archive. And again, the sort of science observation center will allow people to retrieve the data and do their science work. And again, in our case, we also have a WFI instrument science center where there will also be data processing. Now, again, after a long struggle, I got this sort of use case example just to set up the observation from the project scientist. And again, you can see like set up spacecraft parameters, that is to make sure we have the line of sight in the correct direction for the objects they want to observe. And then you can also see that there are a lot of things you need in terms of the instrument that needs to be set up. And again, you will see that like this includes, you have set exposure offset because you're going to receive the messages, and then you're going to need to set up the instrument. So all of these are very important, specifically in terms of how you set up your detectors and define optical path and so on. Now, this is one side of the argument, and that will give me my data and control flow. While on the other side, it's a little bit of a more complicated diagram. And this will, for example, tell me, like from a functional viewpoint, what I need to do. And here you can see, like, during launch, your instrument will be switched off. And I'm just going to go like this. So your very first block you see, it is transition from off to on, and there's certain things your system will need to do. Then follow on, then you will go into a phase of commissioning the instrument. And when that's done, you are ready. And you can then see the next step is, send instrument status information to the mission computer. So by the way, I have to mention, just for not crossing lines and making it even more complicated, I have doubled the mission computer. It's the same thing, just twice, just to make sure that it is neat and clean. And then, they will also send instrument commands for us, to us. And then you will see the next step is execute observation setup commands. Okay, I forgot to say that this now starts touching on things like modes. Maybe you need a standby mode, and clearly you can see, because you're in this holding pattern here, you could call it a standby mode, for example. But I would also like to caution people, think carefully when you define the modes of your system. Too many modes means you are complicating things. Just think about how the control and data flow needs to change between modes. What are the system supposed to do in each of those modes? Because if you've got 5 modes, you need to do your performance testing 5 times. If you had 10 modes, you need to do it 10 times. If you only got 2 modes, you only need to do it twice. So you can start seeing how that is quite helpful to keep a lid on the modes. And then For example, here, prepare observation by executing the setup commands. Now for that, I have a second, you can see this is clearly a second diagram, and there you can see execute observation setup commands. And this is a result of all the things that we previously saw in the use case, where we set up the detector readout sequence, the readout time, observation time, start and stop, default, and things like that. Because in this case, for each detector, we can define up to four windows. Each detector can be read out in full, but you can also, if you're only interested, it's almost like a multi-object situation. You can define the start row of a window and how big the setup is, and that will mean how many rows for each window. So you can see that. But I will focus on the deploy optical element. And again, this, if you look at everything in there, it resulted in what we know as a filter wheel. And you can see all the different things that's listed there will be housed in this filter wheel in there. So this is how you use the functional flow diagram and the use case diagrams and analysis to start implement functionality in hardware and software. Now, I will jump, once you have this, you really can start writing requirements. And writing requirements is actually quite simple, because for each functionality you implement, all you need to do is to know how well you need to execute those functions. You might get functions that is actually more like, like for example, if you go to the ATM, I don't think there is a hard requirement on the delay once you press a button or make a selection, how fast the ATM needs to be. It's not like maybe a hard number, but there might be something that it should be fast enough as not to annoy the customer, and the customer thought nothing is happening. For example, that is why some ATMs will give you a little hourglass to show you that they are busy processing your request, don't worry. So I think that's the thing that is important. Then obviously, in terms of requirements, there's many type of requirements that you have. And these requirements is from functional to performance, environment, handling, and so on and so on. And I think when we talk about requirements, people focus sometimes not on the requirements engineering side, which is the driving and flow down of the requirements, but they focus a lot on the requirement management tools and methodologies. And here I think manage requirements is very, very important. You need the version control, you need to track changes and manage evolving requirements and try to make sure that there's not requirements creep. And in terms of the tools, there are so many tools available that can be used. For example, I've got a lot of experience with Doors and Yama, but every day there's new basically tools available. But it is important to keep your requirements under control, give them unique IDs, and that again go back to basically configuration management. You need to version control your software, your requirements as well. Then finally, what I would say, you can get rid of complexity by come up with simple, elegant solutions, and then to get rid of uncertainty, do risk management, assess your technology readiness level, continuously validating and revisiting requirements, eliminate scope creep, and as I said before, I think eliminate complexity is important, and that is by following a simple design methodology that is underpinned by systems engineering framework. And more important, I know I started from the bottom up, but designing the right product is essential, engaging stakeholders early and often, using a collaborative and iterative process. And I would say, this is me. Thank you for your attention, and any questions?
Just look up the attendees. There are usually questions from there.
I have a question. Okay, please.
Okay, thank you. So the one thing I encountered when I was making attempt to reduce complexity is that when someone other team who I was cooperating with, changing their requirements, it was harder to modify my work than if I were create something more in theory more complex, but that can be adjusted to be required more easily. So how to
Sorry,
compromise?
Agnieszka, for interruption. We can't hear you. There's some noise in the background. If you could just write it down, that would be much simpler.
Okay.
Oops.
Oh, yeah, thank you. Can you hear me? Sorry, Hermine, we can't hear you. You are muted.
Sorry. Yeah, I did muted myself when Agnieszka had so much noise, and I thought if I mute myself, then maybe it will be better. But I'm asking, are people normally so shy in asking questions?
Okay, can I ask you a question in the meantime?
Yeah, please go
Okay,
ahead.
so I just want to because you have a great knowledge about these things, and maybe you can tell us about how it's how is your point of view about projects that are prepared with in the ESA. And because, you know, if we will look on the NASA or Chinese Space Agency or ISRO from India, they are like one organism because it's a one country. They're big institutions. Of course, the financing is different, but still they are working like a one organism as a one country, let's say, facility. And in Europe, we have to combine many countries together, many facilities and institutions. How you are seeing that? Is that really a handicap in our situation, or it's working on our favor? Thank you.
I personally think it is a handicap, because the more different organizations you have working on the same project, your timescales and your cost will increase. And I think, especially on the large missions like a new Athena, it becomes very complicated. Not because of the design, because I heard many people the last 2 years saying that WFI is a complex instrument. And I can assure you from my viewpoint, it's not. But people are using it to maybe justify why we need so many people working on it. But the more people you have, the more interfaces you have, the more opportunities there are for miscommunication, misunderstandings, and things like that. So I do think it makes it more difficult. But then again, I don't know, in terms of the ECSS, if you look at all the guidelines, all the standards, all the requirements, it's massive. And I think it's an overkill. And sometimes, this is my own personal viewpoint, ESA is making things complicated to delay things. We should be a lot faster. I think a project like Athena should not take longer than putting a man on the moon, because there you talk about a human life and lives that were at stake. We are sending a satellite up with just equipment, and it costs a lot, and yet it takes forever. So I think it is against us, but I'm also half wanting to dispute. I think the Chinese are fast. I don't know too much about the Indian, the Indians, if they are as fast as the Chinese, but I think NASA has also slowed down. They had a very good systems engineering handbook in 2005, and it was sort of like digestible. It was a smaller number of pages. I can't remember how many. Now it has grown to the point where it's not understandable what they try to teach you. And similarly, I'm a member of INCOSE, but their book of knowledge is absolutely not practical. There's nothing in there that makes it practical at all. Is that answering your question?
So just want to continue shortly with this. So what do you think it should be a cure for that situation? Do you have any ideas for it?
Well, I would think ESA needs to really get an expert in and really rethink their life cycle model and processes and procedures.
Thank you very much.
Okay, my pleasure. So the one question from, Anikska was first. Complex plan can be easier adjusted to change interlocked needs, then system simplify. I'm finding it hard to really understand the question, because I think if you follow the sort of like slide I had, and now I must actually move this. If you look at this sort of like stepwise process, I think if you follow this, really implementing the functions in hardware and software, and using your use cases to basically drive the behavioral design, if you follow this, then, and you really think about when you start partitioning things, then your system should not be complex. But if you don't do it in a structured, stepwise process, then you might end up with a complicated system and complexity that you don't need. For example, I would put my hand up and say, according to me, what was clear to me in the beginning when I joined WFI, and still today, because sometimes you have to make compromises. The WFI system today, or instrument today, has still too many so-called subsystems in. Actually, the instrument consists of components. And a big example there could be, like, we have a camera head subsystem today and the filter wheel subsystem. And in my mind, that should be one piece of equipment, because a camera head plus the filter wheel, for me, equals to a camera. So immediately things could be simplified. And then again, like you know, we have functionality in our instrument control unit. It will control basically the filter wheel. And ideally, the filter wheel control should have sat with this filter wheel. But again, you had to make compromises because it is guided by who's got enough money. And if one organization do not have enough money to do the complete camera, you have to split it up and then you create interfaces. So I think initially try to come up with a system architecture and not let it be driven by the personnel that's available. I think, but I'm not sure, Aniska, if I've answered your question in any shape or form correctly.
Yes, the question has been answered. Thank you very much. I was trying to write it as shortly as I could in my environment.
Thank you for asking the question. Now, why? There's another question from Rafael. What open source and paid tools you recommend to help in tackling the aerospace project complexity? That is a big question because, again, I would say you need to have like a clear config management system in place. The best we can do in astronomy, because we don't have the money, is to make use of a content management system, at least set that up properly and use it okay. And then make sure that you implement the config management. You know, when something changes, have a process in place, which I would say config management 2 from the Institute for Configuration Management is very good. When I'm doing requirements, I'm used to doors, but I think there are many new ones available. Then I guess also a big question today would be model-based systems engineering, where the work I define here could be, models could be created in MBSE, for example, Cameo. But again, for me, at the moment, model-based systems engineering is nothing really new, but it is you basically each and every block you drew or entity you drew have a characteristics and it's in a database, so you can use that entity over and over again. So I don't really like to tell people what tools are the best, but I use DOORS, and when I do my structural architecturing and my even my behavioral, I use Visio, because unfortunately MB model-based systems engineering tools just, you cannot draw neat diagrams. And for me, neatness is important, not because purely of how it looks, but if you look at the diagram and it's not, it's clear, it should take you a couple of, you know, half a second to a second to really to see what's going on, and not make it more difficult, because a picture is supposed to represent 1,000 words. So sorry, Rafael, maybe you have tools that you want to share with us?
No, not really. I think it's an open issue. So was curious, what are your solutions?
Yeah, I can also tell you when you use DOORS, specifically the non-website DOORS, it's very important to in the beginning define all the properties that you need to track and how you're going to use it, and write a document so everybody who's involved in requirements engineering should be clear on how to use the tool correctly. And again, I think another big problem for us, whoever ask again about ESA, is don't tell ESA this, but I think their way of writing requirements is so unclear and confusing. So there's no clarity. There's no, they know what they want to say, but I think 10 people read a requirement and they will interpret it in 10 different ways. And that is not what requirements should look like, but that's part of our problem, I think. I don't know if you guys agree or not.
We couldn't agree more with what you said, and we're very happy to hear that. On the other hand, talking of standards, you have to follow something, and you have this heavyweight requirement engineering on the part of ESA. On the other side, you have this new space for zero, which I think is a little bit of underkill. What is your recipe for the ideal process that you would see as far as requirements of engineering and systems engineering?
Well, I think I described my ideal system today, and I also think like there's other important points. I do not think that the route that ESA, for example, follow about analysis to the nth degree is the right approach, because analysis is only as good as you can confirm, or modeling, when I call analysis. But when you build a model of your system, unless you build your system, you don't know if your model is right or wrong. So that's point number one. They want you to do so much analysis, and they do not actually promote getting to the point where you can buy or make the parts you need to put your system together. And therefore, the documentation should be agile and minimalist. I need to do only the documentation that really allow me to build, to manufacture, assemble, integrate, and test my system. That, to me, is what it's all about. It's not about creating tons and tons and tons of paper. And actually, I worked on an instrument called Harmony, which is a spectrograph for the European Southern Observatory's extremely large telescope. And at PDR, we had to deliver a lot of documentation. And if we had printed out the documents, the total mass on 100, I think it's at 100 grams, or however they specify the thickness of the paper, we would have ended up with a ton of paper. That doesn't make good systems. Good documentation doesn't need to be overkill. Keep it slim. Is that making sense?
That makes lots of sense, and we really like to hear what you have to say. Listen, I really want to thank you very, very much on part of everyone over here. It was a great lecture, and one thing I would love to have is your archive presentation. If you could send it over, we will put it available to everyone who wants to look at it offline. And once again, Hermine, it was absolutely fantastic, and we appreciate it a lot. Thanks very, very much.
Okay, thank you. I will send a PDF version of the slides to you as soon as I can.
Thanks a lot.
Okay, have a good day. Bye, everybody.
Bye, thank you.
Thank you. Goodbye.